Yep. Hi, all. Glenn Kirshner here. Oh, no, that's a different podcast. Yeah, we're doing some math. All right. So this is a lecture on quadratics. Try to deepen our understanding of what we've been mostly mechanically working with. So this is going to be a little deeper dive into the concepts. And then I'll mention just a few things at the very end of the video of skills and mechanics that you really have to have in order to go up the ladder in the discipline. All right, so let's start with quadratics. Fancy term for rectangles, quad 4 in Latin, right? Rectangles, length times width, get you area, and probably one of the early things that happened mathematically in terms of solving equations was realizing that if you had no area, then you either don't have a length or you don't have a width. That two-dimensional picture disappears. Okay, so those are called factors of the area. But there's one unique rectangle, and that rectangle is the square. And we've been working with that. We've been looking at, changing calculations into squares. It has its advantages. I can't use a square root on a rectangle that doesn't have equal side square lengths. All right, so inverse operations are very helpful in solving a variety of equations, most actually. And I can't, as it's originally written here, x times 10x, which is x times x plus 10. Yeah. Slow brain here, x squared 10x, right? It's been practicing that. It's called factoring. Okay, finding the side lengths of a rectangle. And then we've looked at changing that into a square situation, which actually is putting quadratics in graphing form, which we're going to talk about quite a bit in a moment. All right, many of you have mastered that already, and wonderful. You can now solve this. We can certainly see there's no area here if x equals 0. If x equals -10, you can immediately see that. Over here, it takes a little bit of work. You've got to bring 25 over. You got to take the plus minus square root, which is plus minus 5, and then you've got to subtract 5. And I hope we can see -5 - 5 gets us -10, and -5 plus 5 gets us 0. So that's something we've been working with mechanically. Okay, I got to get this chair down. Got to keep moving the video along the board here. I've got quite a few things already written. Hopefully I won't forget some of the things that I want to say, which typically happens. I finish a video and go, oh, forgot to say that. All right, so we've had this picture on the board numerous times. Looking at user-friendly numbers in the squaring process. -3 times -3, 9, -2 times -2, 4, so on and so forth. And we can see the numbers 9, 4, 1 going down, those area. So if we were looking at the y-axis as being measurement of area, and we start, say, at 9, we go to 4, we go to 1, we go to 0, we go to 1, we go, it's not symmetrically drawn there, 1, 4, 9. We start to see the signature, the numerical signature of the graph. Okay, and quadratics are generally written in the ax squared plus bx plus c form. That's, capturing the multiplication of the FOILing process, 3x plus 4 times x minus 5. You do that out, you get one of those. But we did a month or so ago look at a little physical situation where I took a ball, held it in my hand. You saw me do it. It was 3 feet high, and you saw me in the classroom actually kick that ball straight up without a single bit of spin. 2 seconds later, Maradona-like stopped exactly at 67 feet high and came back down and caught it on the foot. Oh, lovely piece of skill. Yeah. And we had already written at that point, we had been practicing the whole how do you write quadratics given, non-friendly numbers? But in this case, I gave you friendly numbers. We said, okay, well, you got a max. And the maximum occurs when you actually have a minus sign in front of the squaring process. We got a min at 0, so put a minus in front of that to get a max, and it maxed out at 2. So we kind of had that thought process started, that discussion started. Let me get an eraser here. All right, keep this in the old pocket. We said, okay, well, where we go? Where are we at 2 seconds? And we said, oh yeah, we're 67 feet. And measuring from the vertex, which some people have been measuring from the other point in the absolute value problems we've been doing, but you're measuring from the vertex. That's the symmetric change happens from there. And 67 to 3 is actually a drop of 64. That's where that minus sign came into play. We're actually going down 64. And quadratic change is, you go back 2 seconds. If you square that, you should get 4 units of change. But we didn't get 4 units of change. We went down 64. So we've been practicing that. And that's what gave us this minus 16t squared plus 64t plus 3. Okay, and this is the graphing form. And a lot of time is spent and energy is spent in first and second year algebra classes and pre-calculus as well, studying what are called transformations. As you know, I'm not a fan of transformations. I think people initially studying algebra see it as a video game. I do the OYMCA. I don't think numbers shift. I think we measure change from a moment and we try to describe it. I think that's a better way of approaching things. And I'm going to spell out why here in a moment. At least it's my opinion. But where are we at the moment? Still mechanically dealing with this concept of squaring, finding the equations from a graph and so on and so forth, all the stuff we've been practicing. What I'm going to try to do in this video the rest of the way is explain a little deeper as to what's going on and why. Okay? Because you got to tell you what's going on. And then it's just a question of repeating it until maybe you get a chance to see what's going on and why. Okay, so that's an attempt here. Right now we're at minus 16t squared plus 64t plus 3. And of course, if I get rid of this term and I've got the ball 3 feet high and I kick it, it's going up into space at 64 feet per second every second. It's just, 64 feet 1 second, the next second, 64 feet, the next second. It's going forever up. That's just a line. 64, boom. But gravity brings it back to Earth. All right, so we have really an initial condition, an initial force, and the major force of gravity in this situation. And you might ask yourself, what kind of force does it take to escape gravity? People have asked that question, and people have actually answered it. All right, so what's the quickest way to sketch? And what's the best approach, I think, is understanding something about rates of change. That's generally what happens in the first half of a calculus class is you study all about rates of change, at least mechanically. But I'm hoping that we can discuss it in a little more depth than that at this instance. It might help you understand quadratics a little better. All right, so we got this squaring process. I guess I got to come over here. 3 times 3 is 9. And I guess Isaac Newton at some point, at least I read this in a textbook over on the Northville campus. He did something along the lines of, well, how is this squaring process? Because we know it's a continuous process. So how's it changing at 3, 9? And he said, well, let me think of a square that's a little bit bigger than 3. I don't know how many decimal places he used, but I'm sure he started with maybe 2 or 3 and went to 7, 8, 9, 10. Who knows? Because there's a nice pattern that comes from this. And it turns out if you square this, you get 9.0601. It turns out that if you had done 3.00001, 10 decimal places, it would have been 9.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can check it on a calculator. Okay. And after teaching calculus for 3 years, this is what I had pop into my head, was this layering of change. But he sandwiched it. And, if this is going up by 0.0601, I assumed it was going down. I checked it. Yes, that's true. And then what he did is he did y2 minus y1 over x2 minus x1. And he found that it was changing at a 6-to-1 ratio at that instant. which actually happens to be 2 times 3. And I'm sure he probably, did a variety of, I'm guessing, where he looked at, well, at 2, there's an area of 4, and it turns out that there's a 4-to-1 rate of change there using the same analysis. And this is algebra 1 analysis. All I did was y2 minus y1 over x2 minus x1, except over a very small change in area. But it measures change at that spot, tells you how the numbers are crunching there, and we can see them. And it turns out there's a major pattern here. And let's just look at it briefly, because you may not look at it in your calculus class when you get there. And if you don't, you may have the same experience I had of 3 years of teaching something I didn't know what I was looking at, because nobody ever told me a major symbol and what it represents or what it represented. All right, so let's look at just going from 9 units of area to the 9.0601 that we talked about. Well, I guess I got 3 decimal places here now. So I got to do 0.06001 in this instance. All right. So the old dimension was 9, and then I'm pushing it up by 0.001, which obviously is not drawn to scale. Very hard to show that distance. Okay, it's really a layering process. All right, and so if I multiply it times the side length of 3, I get new change in area 0.003. And right here at the cusp, I get 0.001 times 0.001. Yeah, I'm just doing geometry with you here. There's nothing, that's not rocket science. So you get 0.001, which is so small, we're going to just ignore it. All right, and the same thing over here to maintain the shape, 0.001 times 3 gets me 0.003. And we can see that the change in area is 0.003 divided by 0.003, which is 0.006. And if we look at how the x has changed by 0.001, you can see that calculation. Okay, that's algebra 1. But on a conceptual basis, we have this symbol dx, and you'll see it later in your careers. And you can think of it as just a little difference in x. And I don't think that's hard to see. 0.001, it's just a little difference, that this is now a length of 3.001, where it used to be a length of 3. It's just a little difference in, in a number. And it turns out that this formula actually works for all spots on a quadratic. It's 2x dx for this particular graph, which means that at 0, we're not changing much, which brings us back to where we started. Right here. Make the connection. If I add a layer of area and I change by 0.001, well, I can kind of see it over here. If I change by 0.001, I'm not changing the area much, because there's no square. Pretty hard to change something if nothing's there. Okay, I don't know if that made any sense, but at least in this context, perhaps it does. All right, so let's go back now to our ball problem. Let's kick the ball up in the air, and we know there's symmetry in these graphs. We saw it in that diagram just a second ago. So I think this is the best form for graphing a line, the way it's originally written, because I can see the initial amount. So on the y-axis, I've got some place to start from, 0, 3. And I also know the rate of change, because if I'm at 0, there's no box. But if I change by 0.01 here, right, put a 0 into 64t, okay, nothing comes out. But if I put 0.001 in there, then I get 0.064. That's change. I can see it. So I know I'm going up at 64 feet per second. And if there's symmetry somewhere over here, I've got to be going down at 64 feet per second. It's just the way it is. All right, so there's a place in between going up at 64 feet per second and going down where I'm not changing. Okay, well, that's the average. And the average of these things is 0, right? Okay. So there's some number in between. And how do you get an average? You divide by 2. Oh, I hope minus b over 2a is starting to pop in your head because there's a division by 2. Okay. And what else is happening? Well, there's multiplication by negative 16. So I probably have to get rid of that multiplication. If I'm trying to solve a problem, you use inverse operations to solve things. So instead of multiplying by negative 16, I'm probably going to divide. So what am I doing? I'm taking the number 64 and I am dividing it. I'm doing the opposite, right? I'm doing the opposite. All right. So, and dividing by 2 and multiplying by negative 16, solving means dividing by it. And lo and behold, what do I get? I get 64 divided by 32. 2. Okay. And if I put a 2 in here, it's not hard. 2 squared, 4 times negative 16. Am I off the board here? Sort of. So let's do it over here. All right. So negative 16, 2 squared plus 64 times 2 plus 3. And we said there's all kinds of shortcuts to this, right? All kinds of shortcuts. So that's 128, right? Divided by 2 is 64. And then divided by 16, right, is 64 plus the 3. I already did the division. 67. There's shortcuts to that. Take them if you want. I suggest you learn them. And now we've got the graph. I didn't have to put it in graphing form. In fact, I think it's quicker because if I put it in graphing form, then I still got to sketch it. I just ignored the graphing form and sketched it because it actually is already a graphing form. If we look at the transformation, minus 16 times t minus 2 squared, well, let me get an eraser here again. That's a graph. That's one term. Okay, and what's that one term? That one term is moving the graph, shifting it over. This is the language people use. 2 zeros, shifting it over. And then, oh, it's minus 16, excuse me. Minus 16, right? There it is. 2 gets you 0. And we're going down at 16 to 1 initially, and then faster and faster and faster. And then when we add the next term, which is 67, we shift the graph up, right? 2 comma 67. That's the language that's used. Nothing wrong with it. And I understand at some of the higher levels of mathematics, which I haven't done. Good Mr. I got to talk to Forrest, my good friend down at Deerfield. We have this discussion a lot. The beauty of transformations and where you use it. I trust him. It'll come into play. But at this level, I'm still a fan of this because I think you can probably make some more connections. But so is this minus 16t squared. That's a graph. And I think people are familiar with 64t plus 3 from all the mx plus b that everybody's got shoved into their head, right? So there it is. There's 64t plus 3 as a graph right here. All right, and then we know that it gets taken over by the, the gravity here. The force of the kick is certainly not as strong as the force of gravity. That wins out, and mathematically it wins out, right? Because squaring is more powerful than linear as we move away from the number 1. All right, I'm rambling. All right, so let's get back to doing something concrete. I think you should be able to find the sketch, the roots, the range, and putting it in graphing form in all under a minute. So let's practice that. It's still dark in here. I hope that I had to switch to a darker marker because I originally wrote this in the green and I couldn't see it myself. So I'm just throwing some green problems up there. You hit the space bar and see if you can answer all these questions. I guess I got to write the questions again. I want you to be able to sketch. I want you to be able to locate the roots, the range, and putting it in graphing form, just because you probably expected to do that on tests and finals and everything else, standardized tests. All right, so we want to do that. All right, so what do we have here? 4 steps to doing this, and I'm going to talk you through it. Or maybe I should talk you through it after I show you that you can do it in 60 seconds or less. Yeah, let's do it. So let's go with 4x squared plus something that's canned here. Multiples of 4. Let's go up to 24. Let's do a minus sign this time. Minus 24x plus 7. There we go. All right, so we'll give you a shot at that one. And we'll do it together, the 4 steps it takes to kind of get this process started. All right, so what do I see? I see cup shape up. That's 12 going up on the upside. Here's the increasing side. I probably should have talked about that at some point a little bit more. So 0, 3 is on the increasing. So I know my graph here is negative. So I can put a negative x value. 12 divided by 2 is 6 divided by 2 again is 3. That's the x value. Negative 3 times 12, negative 36. I'm going to cut it in half. Minus 18 plus 3 is minus 15. Okay, so what are the roots? Well, I know I got to get to 0. 0's here. So I got to go up 15 units. I know that I got a multiplier of 2. I know it's the square root process, and I'm measuring from negative 3. So that gets me my roots. I can see my y value. So I got my range, y greater than or equal to negative 15. And I can put it in graphing form because I've got the 2 already, and I've got the 3, so that's already given, and I know that I'm at minus 15. I'm done. So that probably took a little longer than it should have, but just to show you that it doesn't take long and it's not rocket science if you practice it. So now let's practice it. I will slow it down, and hopefully I just erased the last problem. So I better put that last problem back up again. Why don't we go with a negative 3? So we'll go with a positive 3 over here. So let's go with 3x squared. So let's go with, I don't know, 24. That's a minus over there. So we'll make this plus 24x. How about minus, instead of plus 7, we'll make it minus 7. All right, so what's the first step? I think your first step is to draw a y-axis. And I think you want to locate 0, negative 7 on the y-axis. And then I think you want to look at the cup shape, and it's a cup shape up. So therefore, if it's a cup shape up, wait a minute, plus 24, I just blew that. Not thinking, so I got to start again. Y-axis, all right, so 0, negative 7. Okay, and I know that I am reading this way. So I'm going up from there. Okay, that's what I talked about before. If I'm going up from there, then it's got to be cup shape up as well because it's a positive 3. That tells me I have a negative here, a negative x value. So I can just divide 3 into 24, which gets me 8, and I can cut it in half, and I know that that's negative 4. Now, if I hadn't have stopped before, I would find my error now. A moment ago, I had made an error. I would capture it now by plugging negative 4 in. Negative 4 squared, 16 times 3 is 48. Negative 4 times this is always twice the size of that. We can look at it geometrically later. Put those first 2 terms together, you get half of the middle term. And therefore, we are now at minus 55. Minus 55. Okay. It doesn't hurt to talk about how you get from minus 55 to minus 7. You got to go up, and you have to go up 62 units. I hope I didn't make a mistake here. Minus 48, minus 7, minus 55 to minus, so no, I did make a mistake. Yeah, it's too early in the morning. Minus 55 to minus 7 is up 48 units. There we go. 48 units. That's what I should have. That's what I have to have change, okay? Minus 4 to 0 is a change of 4 units, but a quadratic, we're looking at the area change, which is 16. And so there is your check of the number 3, okay? But I got off on a little tangent there, especially that is a tangent. A little math joke. All right, so where are we at now? Now we're at, when does this, let's do the graphing form. It might help you see this from a different perspective. So what's the graphing form? Graphing form is x plus 4 squared minus 55, and we already know the multiplier is a 3. And let's set that equal to 0. Okay, well, you'd have to bring the 55 over, right? Because to get to zero, zero's up here. If we're at negative 55, to get all the way up to zero, we got to go up 55 units. We're dividing by 3. All right, so we're getting rid of that, we're getting rid of that. We're taking a square root, plus minus, right? And then positive 4 becomes negative 4. And there's your roots. You can kind of see it if you take a moment. It's all here. You know, we know the A is 3. So those numbers are the only numbers you're working with. So it's not hard to get it mechanically. Where am I at? Oh, range. My range is Y values, all the Y values. This is a Y, that's a Y, that's a Y, that's a Y, that's a Y, right? All those Y values are greater than or equal to negative 55. Now, there's no excuse on problem number 52 to leave it blank on the next test. Yeah, I mean, positive means it's cut shape up. I mean, give me that out of 2 points, and you're going to get at least a half a point. It shows me you got some understanding of the graph. Leaving it totally blank is not acceptable tomorrow. It's not. And if you can simply put the y-intercept on there on the correct side, then you're going to get a full point. You're going to get a check. And if you can list the vertex, then you're going to get the last point, because that is the most important place on the quadratic. So let's see if you can try all those things now. For that problem, and I'm just going to go through it without talking because I'm tired. It's 6:30, okay, and been putting this on the board for a while and thinking about it since 5. So I'm just going to do it and then show you a couple of the skills, not all of them, but some of the skills that are really important for moving forward. All right, so I know it's cup shaped down. I know I'm on the downside, 0, 7. Therefore, I know that this is a negative again. I guess I'm really happy with negatives today. I'm talking, I said I wouldn't. Okay, so 30 divided by 3 is 10 cut in half. So this is minus 5. And if I put that in there, I get minus 150, cut in half, minus 75, plus 7, minus 67. I think I made a boo-boo there. My brain is very slow at the moment. Okay, so that's 68. All right. So what are my roots? Well, I got to get the 0. 0's down here. So I got real roots. And they are, I got to go 68 units. I got to multiply or negative 3. So I got to go down. I got to go down. That's what makes it positive. Thought I'd show that. Plus, minus. And I'm measuring from both sides of negative 5. All right, so there's the roots. The range, y values in this case are less than or equal to negative 68. And the graphing form is negative 3 comma x plus 5 squared minus 68, because we want negative 5 to act like a 0. All right, special case situation. All right, almost done. Running out of gas here. Real quick. The worst way. All right, so 5x squared minus 10. You want to be able to move the 10 over. You want to remember the plus minus, and you want to know that you're divided by 5. But I just butchered that. I told you I'm tired. Almost. I'm not going to do the video again. So you're going to bring that over. You're going to divide by 5, and then you're going to take the plus minus square root. Okay. This one is easier to factor. Take out what's common. Some people would take 5x out. I like just taking x out. It gives me that nice symmetry sense of the vertex. So x, 0, and then I got to get back to 5x squared, and I got to get back to minus 10x. And so we can see roots of 0 and roots of 2, which means that 1 is right in between. All right, so this one here, well, now you see we got to figure out what's the best way to solve that. I think when you get numbers like that, I prefer to put it in graphing form. But we will definitely tackle the quadratic formula. A couple of students have already derived it on their own in class. Other people haven't heard about it yet. So we have a wide range of who's studying what at the moment. But I think it's quickest to do this. If it's a minus, it's a minus. If they're opposites, one's positive, one negative, then it's a negative in there. And then you can just divide 5 into 10. And my brain is really getting tired. And then dividing by 2. So would I want this one divided by 2? Yeah, I guess I would. So there we go. So we got to divide it in, cut it in half, And so now it's completing the square process. If that wasn't there, you just subtract 1. So now you got to subtract 5. And we'll be talking about that in class. I think it's okay for you to do that. With practice, you can write that much more quickly than I just talked about it. So I would allow this in class. And so, you know, what do we have? We got -2. So we got to bring it to the other side, divide by 5, plus minus square root of 1 measure 1. There's your roots. Okay, so keep that in mind every time you get a practice. You get a little faster, a little better, hopefully, a little bit more understanding what's going on. Woo! I gotta go get myself a coffee. All right. Ciao.